Hi everyone and welcome to lightSyntax. This channel discusses algorithms, frameworks, computer languages, software architecture, you name it. I am trying to make a community, a computer science community just for the fun stuff. By fun I mean puzzles, share expertise, make tutorials, etc. Whatever you find fun. I am new to podcasting, so please feel free to criticize me, make requests, send suggestions, comment below, whatever you like. This will help improve the channel. As for me, I am Ahmed Azzat, a 5G software engineer at Dell. I am also a scientific author in IEEE and Elsevier, and if you like lightSyntax, please subscribe, share it with your friends, hit the like button, and to crack things up, we start today by discussing some connectivity problems. Are they connected? Are they not connected? Do they belong together? Is there a way of communicating a message between a sender and a receiver? It's a classical problem in computer science, networking, maybe stability analysis, community research. Let's take some examples. Here are three lovely servers: server A, server B, and server C. A is connected to B, B is connected to C. Obviously, A can talk to C, but how are we gonna deal with that efficiently? If there is hundreds, thousands, millions of servers out there, the problem may become a little more complicated. So, Ahmed, John, and Noah. Noah knows Ahmed, and John knows Noah. By knows here, I mean the relation is bidirectional and transitive. So, if Noah knows Ahmed, in return Ahmed knows Noah. If Noah knows John, in return John knows Noah. And by extension, Ahmed and John knows each other, or at least in the same community. Okay, is there a route from work to home? Are they connected somehow in some kind of road networks? Maybe phone network? Maybe. Road between New York and Tulsa. Is there one? Are they connected? Do we need another? Connections and connectivity. Usually, links are given in these simple forms. Pairs of items. Server A connects to server B. Server B connects to server C. Server C connects to server D, and so on. So, K connects to F, and F connects to C. By the transitivity and the bidirectionality of these links, we know that F connects to A, and let's say X and Y do not connect to C. But is there a way to do this efficiently, let's say in big O of one time? Maybe this. Fortunately, in mathematics there is something called a set. A set usually a group of items or values grouped together. Let's say this is set 1. So, first, each server lies in its own lonely set. But when a connection is established between A and B, we union or merge those sets together into another set, A and B. Let's call it SAB. So, to answer the question if A connects to B, we get the set in which A exists and the set in which B exists, and we check, are they in the same set? If they are connected. If they're not, there is no path between them. So, let's take an example, the example we have drawn here. At first, A, we have A and B, then A, P, C, and D and F, etc. But the question here is, there a better form than this that we can computationally use? There's a form that does not require reallocation of arrays or vectors or whatever container you are using. So we can name each element a node, and at first its node is considered the parent of itself. So when A connects to P, suddenly B is not the parent of itself anymore, but A is the parent of B. And here we go. We need to ask, what is the parent of A? That's A. What is the parent of B? That's also A. So they are connected. At this stage, are they connected to C? No. The parent of B is A, while the parent of C is C. So they are not quite in the same set. This technique connects nodes within big O of one time, just setting the parent of a node. That's easy enough, but the catch here is that this chain can go up and become a huge chain, which does not quite meet the performance requirement we are discussing. To solve that, fortunately, there's a technique, a good one, called the path compression. This path compression technique we can leverage to compress this path. For example, when C connects to P, we don't connect C to P, we connect the parent of C to the parent of A. So this becomes that. And when F connects to C, it doesn't connect to C, it connects to A. And here we go. When we check if A connects to F or P connects to F, we only check what is the parent of P, it's A, what is the parent of F, it's also A, so they are connected. Simple enough. Let's code it. So here we are. I realize everyone may have a different representation, a different way to solve this problem, but this is mine. We're gonna do C++. It's one of my favorite languages. Maybe the next tutorial will be in Golang. Okay, here we are. Class node. What is a node? The node has an ID and a community size. It has also let's take this out, we don't need it. So that's a very simple class. As the constructor we need nothing but to assign its ID and set it size to 1. From the previous slide we know initially each node is not connected. Until such connection exists, the size remains 1. A group of nodes will make up a network. So the network has a constructor. Initially we need to know what is the maximum number of nodes that we have. So the class node also provides some mechanism to add a connection between node A and node B. Also it provides us a mechanism to ask if A is connected to B or not. In order to keep track of the nodes, we have two unordered maps. An ordered map is essentially it's a hash map. Okay, whatever. And also a key tag of the nodes and parents. And the map connects the ID of the node to its parent. To the node, the ID of the node to the node, or to the ID of a node to a parent. Essentially, that's it. So, how do we construct a map? Given a number of nodes, we allocate the nodes. At first, each node is the parent of itself and has the ID of R. So, how do we add a connection? First, we ask, is A connected to B? How do we know that? We know that if the parent of A is the parent of B. So, if it is, there's nothing here to do. This connection does not change the network. Else, we get the parent of A, we get the parent of B, and check. What is the size of A, community A, or network A, or partition A and B? Let's say you found that A is bigger, so for obvious reasons, A should be the parent of B. And here we go. And the size of A thus increases to include the size of B as well. The size of B doesn't have to change because we don't actually ask anymore what is the size of B, we ask what is the size of parent B. If it is not, we do the exact opposite. B becomes the parent of A, and the size of B of parent B increases by the parent A or community A, and that's it. If A is equal to B, we don't care. So, as we did before, this is the means to ask for connectivity. Thank you very much. So, it's simple, isn't it? Please, if you like it, please hit the like button, subscribe to my channel, share it with your friends, whatever you like. If you have comments, kind of criticism, whatever, please let me know so I can be better, make a better content, improve this channel. Thank you very much. Thank you all, and bye bye.